what we're talking about in related rates is how to relate a formula to its change according to time. Its change according to time. For instance, how is cost changing according to time? How is profit changing according to time? How is a volume of something that's expanding or shrinking changing according to time? So what's the volume doing at exactly 3 seconds? Is it expanding? Is it decreasing? At what rate is it doing that? That's what we're talking about here. Does that make sense to you? So I'll give you like an introduction here. This is basically relating a formula with time. That's what related rates mean for us, relating a formula with time. Here's an example. We're not going to work all the way through this example. I just want to give you the idea on what's happening here, and then we'll start with some simpler ones. It's kind of weird. I'm going to start you off with one of the harder examples, and then we'll make it easier. Okay, just so you see the idea first. Let's say that I have this cone. That's my cone here. And what I'm doing is this cone is underneath a faucet. My faucet. Okay, and water's coming out of it. It fills it up to a certain level, and then we take and we cut the cone right there, so the water starts coming out. So maybe this is like some sort of a water container for a city. A huge cone, usually they're probably cylinders, but let's just pretend it's a cone. It's the same idea would apply for a cylinder. But it's going to fill it up to a certain level, and once it gets to that level, maybe it opens up. And that's our idea for this idea, or for this related rates problem. So after a while, I'm going to have some sort of a level of water here. True? And of course that water is going to be, as soon as I open up this bottle, I shut this off, I open up this bottle and start leaking out. So probably pretty fast at first, whatever that takes place, it's going to be leaking out somewhere. Now, our cone has a couple of dimensions to it. What do you need to know to find the volume of a cone?
Radius and height.
We're going to talk about volume here in just a little bit. Okay, we do need a height of the cone. I heard height first. Yes, that's a height. And the radius of the cone is probably pretty important. So you got height and radius. What I want to do is find the rate of change of the volume of the water with respect to time. I know it's a horrible sounding question, right? Find the rate of change of the volume of the water with respect to time. That's our idea. Well, here's our issue. Does the water fill the whole cone up? So that H and that R, if you think about this, the H and the R stood for the whole cone, right? If it were filled up, that would be the water's H and R as well. However, as we lose water, what's happening to the H? Sure, and the R is also decreasing as well, right? So at certain times, this is going to have different radiuses and different heights, and therefore a different volume of water. So we're going to be able to, I'm going to show you how to do this. We're going to be able to find out how this volume of water is changing at any given moment in time. So here's what you need to do. The first thing is find a formula that relates what you want to talk about. So basically, what are we talking about? The rate of change of what?
Water.
So we need a volume. So we need to know the volume of a cone first. So it starts off quite easy. It says, find me the volume of a cone. Now, do you know the volume of a cone? Do you know the volume of a cylinder? Oh boy. Do you know the area of a circle?
Be a third of that.
Okay, let's start there. That's the area of a circle, right? Notice that a cylinder is just a whole bunch of circles stacked on top of each other for however much the height is. So surface area of a circle is pi r squared, therefore the volume of a cylinder is pi r squared times the height. To find the volume of a cone, you cut that in thirds. So it's 1/3 pi r squared h.
Third, okay.
Or pi over 3r squared h. Now here's the deal. This relates what we want it to relate. Look at the board. It relates volume with the radius and the height. That's all of our measurements up here. Are you agreed on that? You got to have that for a related rate problem. But the other problem is there any time anywhere? Now here's how we're going to use implicit differentiation to our advantage. You can take a derivative of this equation with respect to any variable that you really want to. Now some of them will make sense, but we're going to take it with respect to time. So we're going to implicitly derive this formula with respect to time, because that's what related rate does, is with respect to time. So find a derivative with respect to time. Implicitly. Why can we do this? Why is this allowed for us to do? Well, think about it. Is volume changing according to time?
Yeah.
Is the radius changing according to time? Is the height changing according to time? All of those things are then functions of t, functions of time. Just like y was a function of x in our earlier implicit differentiation problems, all of these are now well, pi over 3 is not, that's a constant, but h and r and v are all functions in terms of time. So we can do that, but you just have to be careful, because since these are all functions of time, do you remember that when y was a function of x, you had to take and put a dy dx after everything? Because it was a function of x. Now every one of these variables is a function of time. So we're going to have a d whatever dt after every one of them, because they're all implicit functions of time. Notice how none of these are solved for t, right? I can't say h equals this t, v equals this t, r, I can't say that. So I can't solve them for t explicitly, so I have to treat them implicitly, just like we did in the previous examples. You're going to see this in just a moment. So we can do this because v, r, and t, I'm sorry, v, r, and h, sorry, are all functions of time. So we're lucky that implicit differentiation was such a good lead-in to this. So let's go ahead and do that. We'll take the derivative implicitly of both sides. So when we took an implicit derivative, we did a d something of both sides to start off with, right?
T.
So this would be a d what? T, yt. Yeah. What d dt stands for is a derivative with respect to time, or in other words, it gives you the, listen carefully, the rate of change according to the time. Does that make sense? The related rate, the related rate of change, because a derivative is a rate of change, according to the time. So d dt, sure, of the volume equals, well, d dt of that entire right-hand side as well. Let's start with the easy side. Easy side's the left-hand side. What is d dt of v? What's it? Remember, v is just a single variable.
1.
What's the derivative of v? It would be 1, but then you have the chain rule. Why do you have the chain rule here?
1 times d dt. Because it's a function of time.
Is v a function of t?
Yeah.
So just like y was a function of x and you did a dy dx, v is a function of t. So look what this says. This says the derivative of v with respect to t. This says the derivative of v with respect to t. v is a function of t. So you have to have that. It's implicit. It's the implicit
okay.
way to write, it's stating that v is a function of t. You have to have the dv dt. Here's what this says in English. This says, this is how the volume's changing with respect to time. That's the rate of change of the volume. Does that make sense to you? You see why we need that dv dt? It is an implicit derivative. Now on the right-hand side, what now? Oh, explain. I'm not supposed. Do you see the chain rule here? Chain rule says, sure, it is cosecant, but if there's something special in there besides an x, that means a chain rule, because that's a composition just like this one was, just like, what's the other one? Just like that one was, just like that, this one was. That's a composition. You need a chain rule. Here's what this says. So today, inside here, those variables. Yeah, you got to solve it. This part is coming from the same idea as this right here. It's the chain rule. You bring it down, you subtract derivative of the inside, and that's what we're doing. Derivative of the inside in this case is d dx of y. That is dy dx. That's that piece. dy dx, v is a function of t.
Product rule. So I wonder what we do with these derivatives here on the right side. Before we could just solve for y. Can't do that now. Solve for dy dt dx, I guess. You can't do that.
T. So look what this says. This says the derivative of v with respect to t. This says the derivative of v with respect to t. V is a function of t. So you have to have that. It's implicit. It's the implicit way to write, it's stating that v is a function of t. You have to have the dv dt. Here's what this says in English. This says, this is how the volume's changing with respect to time. That's the rate of change of the volume. Does that make sense to you? You see why we need that dv dt? It is an implicit derivative. Now on the right-hand side, what now?
Product rule.
Oh, explain why I need a product rule.
Multiplying a function by another function.
Okay, so what are my variables over here? Are each of those a function in terms of t? Yes, I said all of them were. So if we're taking this with respect to t, that's a function in terms of t, that's a function in terms of t, and they're being multiplied. That means the product rule. How many will see the product rule up there? Okay, let's do it. You said the product rule. You can do it one of two ways. You can take the pi over 3 out, or you can associate it with one of the variables. It really doesn't matter. I think I took it out. I don't know why, but it really doesn't matter. Okay, let's see. When you do this first derivative, this part's going to give you 2r. What
Times
else do I need
drdt.
besides the 2r? Oh, besides the h. I need dr dt. Did you guys all have dr dt? It's implicit, so you have to have not only 2r, and not only the h, but you're going to get actually, you know what, I'll write it this way so you see it. This gives you the 2r dr dt times h. That's this piece right here. That's what that gives you. Then the plus, this is going to give you r squared, sure. What's the dh dt? What's that going to give you?
dh dt.
There's dh dt. Show of hands, how many people got 2r dr dt and then h, and then the r squared dh dt? Do you all get that as well? So if we pretty this up just a little teeny bit, I'll probably put the h in front of the dr dt just because that's how we like to write it. So 2rh dr dt
It's a long
plus
example.
r squared dh dt. Now, if you didn't pull out the pi over 3, you have a pi over 3 here, and you have a 2 pi over 3 there. Is it any different? No, it's the same thing. What I really want to you look at, we're not going to actually do an example of this one. I wanted you to get this
What?
idea down. But here's what we would have to know in order to figure this out. If I said, how is the volume changing, or what's the rate of change in the volume at, and inserted this question to you, I'd have to give you a lot of information. You see, we would have to know not only the R at that time, not only the H at that time, not only the D, we need to know the dr dt. So we'd have the R, that's the radius. We'd have the H, we'd have the height. But we'd also need to know, well, we need to know dr dt. What is dr dt? Sure, but what's it mean?
Change in the radius over time.
How the radius is
Rate of
changing
change of the
with
radius.
respect to time. Does that make sense? It'll either be growing or falling, depending on whether we're putting water in or taking water out. But the radius will be growing or shrinking. So we need to know the rate at which it's changing for a moment of time. We need to know that. That will tell us how the volume is changing in a moment of time. We'd also need to know dH dt. What's dH dt stand for?
Change in height.
Change in the
Yeah, how the height of our water is changing with respect to time. Is it going up? Is it going down? What's happening to that? We need to know all of those pieces, what the radius is currently, what the height is currently. That would give us the actual volume. But to associate how the volume is changing, that's where we need the change in the radius and the change in the height. Help people kind of understand the concept of our related rates. Now, we're going to go a little step backwards and kind of start simply, and we're going to build up to problems like this. Are you ready for it? But if you understand this, you understand the concept. So let's start off real simple. I'm not even going to give you any background on this. I'm just saying, here's an equation.
Easy one.
Find dy.
All right. Well, you know what? It's okay, so if it's dy dt, that's only on the right side. Because it would be like dy dx, kind of. The derivative of the function with respect to t. So it's an explicit.
dt, and here's what this implies. It implies that y and x are both functions in terms of t, just like this was. Okay, it implies that y is changing according to time and x is changing according to time. Are you with me on this? So they're functions in terms of t.
Oh, at
T equals 1.
Is there more information? Because, like, what? I don't think you can do anything. with this.
Why don't you go ahead and do this real quick for me? Take an implicit derivative, because this has to be implicit. Y and x are in terms of t right now. It's got to be implicit. Take an implicit derivative with respect to t right now for me.
I guess y does just mean function, not like, okay.
There's no hard product rule. There's nothing about this. So d dt of y equals d dt of x cubed. Notice we're taking to respect to t because we want to figure out what happens here at dy dt and at t equals 1. So what's this side going to become for you?
dy dt.
On the right-hand side, I get 3x squared, right? And that's it? Y dx dt. Look at it. Look at, I know we have an x up here, but are you taking it with respect to x? No, you're not. You're taking it with respect to t, implying that x is a function of t. So unless there's an x there, you have to have something after that. Just like we had a dx of y, we had to have that dy dx, right? It was in terms of x. So this says I need a dx dt. Show of hands, function of t. So unless there's an x there, you have to have something after that. Just like we had a dx of y, we had to have that dy dx, right? It was in terms of x. So this says I need a dx dt. Show of hands how many will have that. Good, you understand the implicit form of this. And that's what that means. So let's go ahead, let's figure out what happens at t equals 1. Oh crap. Where do I plug in the t? Is
Can't.
there a t to plug in?
No.
By the way, you can't plug in. Can't plug that in. D1. I sunk your battleship. That's what that means. No, there's. Did you get it? That was funny. No, there's no T to plug in. So if I give this problem to you, I have to give you more things. I have to give you stuff. I would have had to give you all this stuff, right? It has to be given somewhere in the problem. So here's what I'm going to say. Find this out if x equals 2 and dx dt equals 4 at t equals 1. At t equals 1.
Jeez. So this would be the rate of change of the x with respect to t, which is 4. So the rate of change with the function with respect to t is 48.
note something please. X and dx dt will change for certain times. So at t equals 2, this would no longer be the case. But look what I've given you. I said find it at t equals 1. Oh, what's happening at t equals 1? I've also given you that information. Does that make sense to you? So I've given, it matches up. I've given you the piece for that. So why does it say t equals 1 and t equals 1? It says find this at t equals 1, yes. But then I have to tell you what happens at t equals 1. I can't just give these to you unless I define t equals 1 either, because those things will change for other times. Now do you have enough information to plug this in? You got an x, you got an x. You got dx dt, I have the rate of change of x according to time. That means you can plug in the numbers and figure this out. So this would be what is it? 48 units according to whatever time, like seconds or hours, according to whatever t is. What does this mean? This means that y is changing at a rate of 48 whatevers per unit of time. That's what that says. You okay with this? Cool, all right. Let's intensify the problem just a little bit. So next thing we're going to talk about. Have you guys ever heard of the Exxon Valdez?
Yes.
What did it do? Oil spill, yeah. And oil is crazy, right? Because it usually sticks on the surface of water and just starts expanding. Just keeps on expanding. Now we're going to do kind of a simplified problem. You see, in the ocean, there's current and there's drift and there's waves and stuff. We're going to do a simplified Exxon Valdez. What we're going to say is that this small, it's a small tanker. It's not going to be, we're simplifying the problem here. It started leaking oil, and what it's going to do is give us a radius that's spreading at a certain rate. We want to find out how fast the area is increasing at a certain radius. So we want to be able to calculate, model what the surface area of this oil spill is actually going to be. Do you understand the question here? So let me write this out for you real quick. Oh, by the way, any questions on this one? Too late. Oil spill. Here's what we know. Radius is spreading at a constant 3 feet per second. This is one of two cases because naturally, if you think about an oil spill, the radius should actually slow down, right? Because that area is getting massive after a certain amount of time. So the radius should actually slow down spreading. So one of two things is happening. Either this is for a very small oil spill right at the beginning, or for a certain segment of time, which that could be the case, or an instant of time, or the oil is pumping out more and more and more and more. Okay, so you start with a little spill and then you get more. But in any case, we're saying the radius of this circle of oil is a constantly, the radius is growing constantly. Okay, so a constant 3 feet per second. Do you see why that would probably not be realistic unless you have a massive amount of oil that starts real small and then really grows? Do you see that? It's, 3 feet a second, like here's your first circle, and then after 1 second, it is now 3 feet more. So can't even do that. Okay, big. And after another second. So probably over a certain segment of time. What we want to know is how fast is the area increasing when the radius is 30 feet? How fast is radius increasing when, how fast is the area increasing when the radius is 30? Here's what you do first. Number one, you assign some letters to take care of these things. So, firstly, we need this according to time. So we're going to...
It's constant though. How fast is area increasing when r equals 30? Should be 3 feet per second.
Quick t for time. What other things do we need to know about this?
Area.
What now?
Area.
Area. So let's pick A for area. Okay. What else do we need to know about this?
Radius.
Well, that's our ultimate question, right? But I mean just the variables that we're dealing with.
Radius.
We have a radius, so R for radius. So the first part really shouldn't be that big of a deal. Just pick out some letters. So T is going to be your time. In our case, we only have two other things that are happening. We have a radius and we have an area. That's it. Are you guys okay with the letters? Next thing you got to do, after you assign your letters, identify the formula that you're doing. So this is step one. Step one is pick your letters. Step two is you got to identify what formula you're dealing with. And it should be given up there somewhere. It should have some relationship that relates all of your letters, or everything except for T. It should have that. So what are we talking about here that's going to relate our area and our...
Area equals... Wait, how fast is area increasing? Oh, not radius. Okay, that's why. Wait, is this area equals pi r squared be pi 3r squared? Or like pi 3r, or yeah, it's the same thing. And it'll be 3 times the radius. Let's see.
Radius. That's what we really want to do, because the T is going to take care of itself when we find a derivative. We want to relate an area and a radius. Can you think of a formula that relates that? Yeah, it's a circle, right? It's a circle. So in this case, our formula is not very hard. It just says, can you relate everything up here? And that's the idea of a related rate. It says, relate these items I want to compare. And so for us, sure, I have an area and a radius. Let's relate the area of a circle and the radius. Well, that just says area equals pi r squared. That's what we're talking about. You okay with this so far? Now, dA dt is going to come about this, but that's what we're asking. How fast is the area increasing? That's going to be this dA dt. What else are we going to get up here? Do you see the dr dt coming about? So every variable, you're going to get that. dA dt is the rate of change of area according to time, of course. And we're also going to get a dr dt. Now, your problem's not going to give you specifically what dr dt is. And I can say dr dt is this, but it would be worded in such a way that you should use specifically what dr dt is. And I can say dr dt is this, but it would be worded in such a way that you should be able to understand it. What does dr dt mean?
rate of change
Change in the
of
radius.
radius.
Good, good. It means a change in radius. A d, whatever,
It's
that's the
3.
change in radius. By the way, do you know what dr dt is going to equal for our specific problem right here? It should say in the word problem. This says the rate of change of the radius.
feet per second.
What's the rate of change of our radius? Is it 30?
No.
That is the radius. What is the rate of change of the radius? It should be how the radius is changing. I'll put it up there somewhere. It says the radius is spread. Oh, it's changing at a constant of 3 feet a second. So our radius here is changing at a rate of 3 feet per second. Do you understand how to get the dr dt and identify that that's 3 in
Oh
this?
wait, yeah, we can plug that in. And we also have the radius, which is 30.
This case. So it says the radius is changing. Hey, that's a rate of change. That's what we're talking about. Now, after this, we're almost done. The only thing that we've got to do now, step number 3.
Is this feet per second? Yeah, it's.
Take a derivative with respect to time, implicitly, because they're all functions of time. And then lastly, plug in the values and you'll have it. So here's what we're going to do. We'll do it very quickly. We're going to take d dt of a. We're going to take d dt, function of time, of pi r squared. There's no tricky rules involved here. This is going to be dA dt. On the right-hand side, we have 2 pi r dr dt. Do you see where we're getting the 2 pi r? Explain to me why I don't have a product rule between my pi and my r. Why not? Pi is actually not a variable. Yeah, it's constant. So this says bring down the 2, great. Subtract 1 from the exponent, got it. But I need a dr dt. Do you see why I need a dr dt? I've got to be able to incorporate this information somewhere. Do I need to plug anything for dA dt? No, that's my question. That's why I have it over here. So you're going to have everything plugged in except for the main thing you're looking for. In our case, we want just dA dt. You have to have all the other information plugged in. Are you with me still so far? Do I have everything else? Do I have an r? What does it say my r is at this certain time? So when this time comes about, my radius is 30. I don't even care what the time is, do I? Don't even care. My radius is 30. Do I have a DRDT? 3. So we're going to have 2 pi times 30 times 3 feet per second. In fact, I'll use the unit so you see it. 30 feet, right? 30 feet times 3 feet per second. Why am I showing you this? Well, we should end in an area, right? Can I say the area is increasing at 15 feet per second? No, because that would be
Square.
linear. Area should be in square feet, right? Are we going to get square feet? Absolutely. So we're going to get, oh, what is that? 180? What we just found out is that for this specific oil spill, our area is increasing when our radius is 30
About
feet.
pi.
Our area is increasing at 180, unless I did that wrong. Well, I forgot my pi.
That's important. Yeah.
That's a factor of 3.141592, right?
Is that an okay answer, or do you want the decimal?
This is great. Yeah, now if it asks, it could give you something more realistic in the back of your book, but this is exact, a pi would give you an approximation. It says that multiply 180 times pi, that's how much a square footage is increasing per second at this exact moment in time, and that's what we're talking about. Do you guys understand the idea of related rates? We're going to try maybe 1 or 2 next time, not a whole lot, because this is basically the idea. It's an implicit derivative just with respect to time. The problem's going to give you everything else. All right, our last related rates problem. Here's the idea behind this problem and behind every related rates problem. Basically, we're trying to relate a formula that has all of our pieces of information together, and we're trying to relate it to time. So we're taking derivatives with respect to time in order to figure out rates of change. And that's our whole idea, rates of change with respect to time. So in our problem here, here's what's going on. You're launching a rocket from the ground, and you're going to televise it. So what you want is this automated camera. And you're going to set it up at ground level, and you want to make some computer program that's going to watch it. It's a very sturdy camera. Have you ever seen the people watching rockets and they've all zoomed in? It's like, looks like crap. Right? You don't want to be that guy. So you're like, well, you know, we're math dorks. So you want to set up this automated thing that's going to go, and the angle is going to be perfect to keep that rocket centered in its graphic the whole entire time. You get the idea? That's the plan. So what we want to do is, if this rocket is climbing at 600 feet per second when the rocket's at 4,000 feet, how fast will the angle of elevation have to change at 4,000 feet to keep up the rocket? Well, now here's the deal. When we...
Okay. 600 feet per second. So that's the height then. dH/dt equals 600 feet per second when the rocket is at 4,000 feet. Oh, only when the rocket's at 4,000 feet though. And it doesn't matter. The height is 4,000 feet. How fast will the angle of elevation have to change? Angle of elevation. What do we call that for a variable? So it's asking for the rate of change of the angle of elevation at 4,000 feet. But I don't know what angle we'd use for that.
Start out,
So,
this
variable.
distance is going to be fixed, and let's say that we're 3,000 feet away from the rocket. So our camera's not going to move, and the rocket is going straight up. Did you get the idea? Now, because we have this rocket's height, the rocket's height is going to be changing. Are you with me on that? So we can't just call this 4,000 right now. We do have to call it h, because that is a variable that's going to be changed throughout the problem. So our rocket's way up here. I don't know how to draw a rocket. Rocket. That looks like an arrow. I don't know. Rocket. Whatever. I'm close to a rocket. It's a flying arrow. I'm a math dork. Okay, so we've got this rocket flying. It's going to be h feet high. We're going to figure out when h is 4,000 what we're going to be doing on this. But when we come up with our problem here, I told you there's a few things we need to do. The first thing we've got to do, assign some letters. Assign some letters to what we're working with. So, of course, we like to have, what's one thing that we're going to be relating? Time's definitely one of them. So T for time. What's another letter that we might use?
Height, h.
Good. Height, h, we've already have that on there. So h for height.
Angle of
Anything
elevation.
else that we need? We have the time, we've got the height, there's one more relationship up there. Was it? Not acceleration. The what?
Angle.
The angle of the television. So we have to have something to do with the angle of this.
Theta, true.
Let's see if we've related everything in our problem. Here's where you read through your problem carefully, okay? If we've missed anything, if we left anything out, then we haven't assigned enough letters. A rocket's climbing at 600 feet per second. When the rocket is at 4,000 feet, that's a height. We have something for height. How fast is the angle of angle of elevation? That's our angle, so we needed to have that. How fast will the angle of elevation have to change? That fast, that's a rate of change. So we need something to do with time.
Derivative
So we
of
have our time up there, we have our angle up there, we have our
theta
height up
with
there.
respect to time.
Okay, this is back to our height. So we have all the letters that we're going to need right here. Are you with me on this? Now, we don't necessarily have to have a t in the formula we're about to write because we're going to take a derivative with respect to t. We don't need the t, but everything else must be related. That means I'm going to have a formula that relates the height and the angle. Does that make sense? So if I call this my angle of elevation, if I call that my angle, I need a formula that relates height and angle. I need to have that. Is it Pythagorean theorem? Because you know what a lot of people do? They go, oh, right triangle, Pythagorean theorem. That covers everything. Does that cover everything? No. That relates this and this and that, but it doesn't relate to angle, which is our main question, right? So if you use Pythagorean theorem, sure, you can come up with a formula.
Trig.
And sure, you can work some of it out, but it's not
Should
going
be
to have the angle relationship that we are looking for.
Tan-
Are you with me on this?
tangent.
So, can you tell me what incorporates an angle with this? What is that?
Inverse sign.
It doesn't have to be
Inverse.
inverse. It doesn't have to be solved for theta. It just has to have theta in it. It just have the height in it. Okay? Tan. Tan would do it. Tan is opposite over hypotenuse, yes?
Adjacent.
No, it's not. Opposite over adjacent, yeah. What is opposite over hypotenuse? What's adjacent over hypotenuse? On the stretching, got you. Yes, tangent is opposite over adjacent. So does our tangent of theta have to do with the material that we have on the board right now? Are you seeing where I'm getting that from? So tan theta equals, okay, what was it again? What over what? Which is specifically in this case what? Does that relate everything we wanted to relate? Does it relate the angle and the height, basically, is what you're asking?
Yup.
Are you okay on where that's coming from? You've got to have an angle down there somewhere that's typically dealing with some trigonometry. It doesn't involve an angle, you probably don't have to use trigonometry. But this one, we certainly do. Now, the next thing after we assigned our letters and we made our formula was what? What did we do?
Find the derivative of theta with
Okay,
respect to
so we
t.
took a derivative of time. Actually, before that, we identified any rates of change. That's what we did as well. So let's identify any rates of change that we have. Can you read any rates of change, right?
Height,
Any rates of change?
d,
That's a rate of change,
T.
sure. What is changing at 600 feet per second? Is it the angle, the height, or the
Height.
time? What is it? The height. Here's how you write that. If your height is changing with respect to time at 600 feet per second, what would the change in height compared to time be? What is that? Yeah, dHdt, that works. This is the change in height with respect to time, and you know that's 600 feet per second. Actually, we'll get a little bit more fancy. Is it a constant 600 feet per second?
no.
It doesn't say that. So
Only at
this
4,000
is
feet.
specifically at 4,000 feet. So it's defined at 4,000 feet that it's climbing at 600 feet per second. Rockets, when you have a source of propellant, they don't climb at the same rate. Typically, those rockets that take off from the ground increase speed and increase speed and increase speed and keep going and going until they reach their escape velocity and finally they're gone. Does that make sense? So right here at this 4,000 feet mark, we're increasing at 600 feet per second. That's our change in height compared to time.
H is 4,000, right?
The height at when h is 4,000. Yeah, exactly right. When h is 4,000. Let's go ahead and let's try to find this. What we're looking for is, okay, well, we want one more thing. How fast will the angle of elevation change? That means, how can I write how fast will the angle of elevation change? What is that?
E theta d.
d theta dt. That's the change in the angle compared to time. Does that make sense to you? The change in the angle, this is how fast will the angle of elevation have to change. That's the change in the angle compared to the time at 4,000 feet. This is what we're looking for, right there. I'm going to kind of recap just a little bit to hopefully one more time go through this with you. So what we do, usually you can have a picture, something to do with the picture. Here we have a triangle because we're launching a rocket, and we have this angle elevation where the camera's watching the rocket go up. Just hopefully nice and keep it centered in the camera space. Are you with me on this? So we identify everything that we need to do. We have our height, we have our angle, we have our time. That's fine. Come up with a formula that relates those things. That's really on you guys. The formulas usually aren't.
Quotient rule. So derivative of 10. Secant squared x theta. I forgot this is a chain rule. D theta d2. So I'll have to divide this on both sides. So it'd just be 3,000 on top, wouldn't it? $9,000,000? Three, yeah. Okay.
Aren't horribly bad, but you gotta find one that works for you. In our case, we know that tangent of theta is height over 3,000. 3,000 was a constant. H, that's one of our variables we need to relate, so that does it for us. Then we go ahead and we identify what our rates of change are. The height is gonna be changing at 600 feet per second. This is the change in height compared to time. 600 feet per second.
That is in row. With H. Mess that up. So this on the left was right. $3,000. This is DHT2. What's the 600? .2 over secant squared theta.
Per second. What we're looking for is the change in angle, right there. The change in angle with respect to time. Both of them have to occur when the height is 4,000 feet. Because maybe that's our marker we want to make in our computer program. That's an important place for us. I don't know, I don't do computer programming, but maybe that would be important for this particular one. What do you do now? What do you do now? We have our letters assigned. We have all of rates of change done, and we're looking for this thing. We have our formula. What do you do to this formula? What are you going to do?
Take the derivative.
Yeah, take a derivative. Let's go ahead, let's take a derivative of this. a derivative of that with respect to what?
T. Time.
Let's do it with respect to time. So this is implicit differentiation with respect to time. Go ahead and do that real quick, or at least get started on it. Here maybe as a hint for you, if you're struggling with the h over 3,000, you could write this as 1/3000 h to make things a little bit nicer. Really wouldn't matter all that much, but you could do that. You could do that as well. That'd be fine. Now, before we get going, I didn't get a whole lot of enthusiasm on this side of the board. Are there any questions over here? Are you okay that we had to identify h and theta and t? No? Yes. You sure? Are you okay on seeing where the tan theta equals h over 3,000 comes from? By the way, the reason why we get this, the reason why we do this ahead of time, is because this is going to be part of our problem. You're going to have a d variable over dt for every variable that you have. So when we have h and we have theta, you're going to have a d theta dt. In fact, that's what we're counting on. That's what we're counting on, because that's what we're solving for. But you're also going to have a dh dt. So you need to be able to identify that, and that's what we were looking for. So that's why I have a dh dt right here. That's why I know I'm looking for a d theta dt. You're going to have one of those for every variable that you have, because it's all implicit. They're all functions of t. We're just going to feel okay with what we're talking about so far. All right, good. Now, hopefully you made it just past this. Just past this would be, okay, let's take the derivative of tangent theta with respect to t. Keep in mind, this is a chain rule every time because it's with respect to t. So the derivative of tangent is what? Secant squared what?
Theta.
Good. Theta, and then is that it?
D theta dt.
Because you touched the theta with a derivative, you have to have d theta dt. So far, so good? All right. Now, other side. What is 1/3000th h when I take a derivative of that? The constant's there still. Good. Why dh dt?
Because it's in respect to time.
Okay, so h is a function in terms of time, so you absolutely must have a dh dt. Hey, by a show of hands, how many people got that? Good, if you didn't get that, and that some of you didn't raise your hand, if you didn't get that, are you okay on getting secant squared theta d theta dt? You see where that comes from? Every time you take a function of theta with respect to time, you got to have a d theta dt. Are you okay on the 1/3000? That h that has an exponent of 1, bring down the 1, take 1 away from it, that becomes that h to the 0, that's 1. But you need a dh dt, that's a must. You okay with this so far? All right. Well, now we're pretty much almost done when you think about it. Which piece are we ultimately looking for? This is not what we're looking for. We're actually not even looking for the theta, because that's the angle. We're looking for the change of the angle over time. We're looking for this piece. How fast is the angle changing over time? You follow me? At when it's 4,000 feet. This is a constant, and that we have a relationship at 4,000 feet. You with me so far? Okay. So this one's going to be easy. We already have that. This one might take a little bit more work. Let's talk about secant squared theta for a second. First thing I need you to understand is that secant squared theta really means not that.
Secant theta times secant theta.
Means secant theta squared.
Oh, or that.
Keep in mind this is all occurring at 4,000 feet. So let's go back over to our picture here and kind of fill in the blanks a little bit. This is 3,000. This h at a specific time will be, how much are we looking at?
4,000.
That's going to be 4,000 at the moment of time that we're looking at. You follow me on this? That's going to be 4,000. Someone who knows something about Pythagorean triples, tell me if this is 3,000, 4,000. Very good. If it wasn't 3,000 or 4,000, you'd have to do Pythagorean theorem to figure out that distance. By the way, the reason why we're figuring out that distance is because we have to now find what secant theta is. Secant, what is secant? 1 over cosine. So if you found cosine here and just reciprocated, you would get secant. Are you with me on this? So let's go
5,000
ahead, let's
3,000.
talk about what cosine is. What's cosine of my angle theta? What's cosine? Oh, come on, don't leave me hanging. What's cosine here?
3,000 over 5,000.
Good. Specifically, what's cosine? 3,000 over 5,000. Therefore, secant is 5,000 over 3.
This is in seconds, right? Yeah. .072 degrees per second at 4,000 feet.
3,000. Does that make sense to you? 1 over cosine, right? So secant would be reciprocate fraction. You're going to get, instead of 3,000 over 5,000, secant theta will be 5,000 over 3,000.
Or 5 over 3.
Or 5 over. Don't forget that you're squaring it. Are you okay with this so far, folks? Do you see where the 5,000 over 3,000 is coming from? Do you see where the squared's coming from? Now I'm missing something. Let's do the DHDT right now as well. How much is the DHDT that we were talking about? Because when we're at 4,000 feet, we're saying, okay, now we're 4,000, give me the rate of change of height with respect to time, and that's what this is saying. What's the rate of change of height with respect to time? What do we mark that out as? Let's make this a little bit prettier. Can we do that? Make it pretty. What happens over here, 5,000 over 3,000? I love that. That's nice. So I'm going to get 5/3 squared. Over here, we're going to get Did you notice something here as well? Look at the board here real quick. Did you notice how I didn't really divide by secant squared? I just plugged the numbers in. That's okay to do. You can plug in the numbers whenever you want to. You're just going to have one variable remaining, right? Your d whatever dt. You're just solving for that. It doesn't matter when you do it. You could have divided both sides by secant squared theta, and it would have worked out just fine. You're just going to get a complex fraction there. I wanted to save ourselves some trouble and just do it on the left-hand side. All right, are you still okay with this? All right. Let's go ahead and square it. What are you going to get squared? Times d theta dt, which is what I'm looking for, equals 1/5. Let's get rid of 25 over 9. You do what?
Division.
Say what? Okay, very good. So if I multiply by 9/25 on both sides, I'm going to get the 9 over 125, and keep in mind, all this happened when the height was 4,000. That's how we came up with our secant. That's how we came up with this thing as well. So it was dependent on that height. Are you following me on?
Okay, it's the same thing. Same decimal.
The 600 feet per second only works for a height of 4,000. The secant theta only works for a height of 4,000. That's the specific distance we were at, specific height. So that was when the height was 4,000. I know that's small up there. I don't want to write it too big to let it take over the problem. I'll write it so you can see it, 4,000. What now? Can you tell me what we just found?
Rate of change.
Rate of change
Slope,
of the
sure.
angle of elevation.
But in this context, it's a rate of change. A derivative is a rate of change. So this derivative says the rate of change of the angle with respect to time. How fast the angle must change in that moment of time, in this specific moment of time, to keep up with the rocket. Are you following that? So how fast the angle must grow in order to keep up with the rocket at that moment. Before that, maybe quicker. After that, maybe slower. But in that moment, that's how fast it needs to be climbing in that instant of time. Raise your hand if you understand the idea. Okay, now let's make this a little bit more easy to understand. Do that division. How much do you get? Don't all talk at once here. 0.72 or something like that? 0.072. This right here, what you just gave me, is going to be in radians per second.
Oh, radians. Not degrees.
Radians per second. Could you please translate that into degrees? So, because we typically, if I say 0.72 radians per second, you really can't grasp that, can you? It's hard for us because we don't really deal with radians all that much. Translate that into degrees for me. That means
what is it? Pi. (180 over pi). that makes more sense.
You'll multiply by 180 and you'll divide by pi. Multiply by 180, divide by pi, you get
1.125, and carries on up to
4.13.
that. Yeah, that's what we're gonna do.
0.72 radians is 4.13 degrees per second. Is that more understandable? 4 degrees? So at this moment of time, so the rocket takes off, right? Climbing 1,000, 2,000, 3,000, gets to 4,000 feet. That camera better be keeping up with it at a growing, increasing rate of 4.13 degrees per second. So it's got to climb 4 degrees in that 1 second. At that moment of time, now it's not even going to pass a whole second, but at that moment, it's climbing at a rate of 4.13 degrees per second. Do you guys understand the idea? Is the math all that hard? Not really. This is probably the hardest part right there. And that's what's going to be hard for you, is coming up with a formula. Figuring out how to relate these pieces together. After that, look what you're doing. You're just taking implicit derivative. You're just deriving it, making sure you have a d variable over dt for every variable you have. Everything else will be given to you. If not, you can find it with your relationship and then plug the numbers in and it'll work itself out. Any questions on what we've talked about so far? Do you understand what we've talked about so far? I've been doing all the talking today, so any questions before we continue? Sweet deal. The next thing we get to talk about is chapter 3. We're going to skip section 2.9 for right now. We might come back to it. It's called differentials and linear approximation at the end of our class. I hope it's you. More than. More than halfway done.
Really?
Chapter 0. Chapter 1,
Wow,
Chapter 2,
you're right.
3, 4, and part of 5. So, more than halfway. Cool. Chapter 3, specifically 3.1. Today we're going to talk about increasing, decreasing, and concavity. We're going to try to get all those things accomplished in the time that we have. Let me give you an example, a graphic example of increasing and decreasing, just so you understand. And kind of the idea of what's going on. Let's suppose that we have this function. Just like that. And let's say I break this up, and this is that. What I'd like to find out is where this is increasing and where this is decreasing. And more specifically, what the slope is doing at on those intervals. And that's kind of important for us. So the first question is this. Can you give me, increasing means going up, decreasing means going down as we're going from left to right. We read our graphs left to right. So can you give me an interval on which this function, let's assume it's a function, on which this function is increasing, going
A to
up?
B.
Certainly, from A to B.
C to D.
Do you see how from A to B we're rising? From A to B, the function is climbing from A to B. For sure. We're going to use open intervals because at B something special happens. At B it's no longer increasing. We'll talk about that later. How about another interval? Do you have another interval where we're increasing? C to D works, good, because from here to here we're growing up. Growing up. This function's getting so old so fast. How about from D onward? What's happening there? Is it increasing?
No.
Is it decreasing? Okay, constant, very good. Any areas, intervals that are decreasing?
B to C.
For sure, B to C. D onward's pretty boring. D onward's just a constant. The slope is 0, it's going to stay 0 forever. What I do want to talk about are the slopes of the increasing and the decreasing intervals. What's happening to that function on those intervals? Let's look at A to B. What would you say with the slope B for this point? And I don't mean like, oh, this is about 3 over 1 or 5 over 1. I don't care about that. What I really care about is whether it's positive or negative. So,
Positive.
is the slope here positive or negative? How about here? How about here? Hey, how about at B? That's why B is not included, right? So from A all the way to B, would you say that we have a positive slope? Do you understand that when I have a positive slope, that means that my function is actually climbing? Do you see it? Look again from C to D. Let's look at C. At C, 0. But just past C, is that positive still? Positive, positive, positive. It's still positive all the way up until the point D. You follow me on this? When we say we're increasing, what that means for us as far as a derivative and the relationships that we're building in this class, that means that your slope is positive. So increasing will happen if your slope is positive. There's no way you can draw a positive slope and not be going upwards. Are you with me on that? If you draw a positive slope, you're going upwards. True? Even if it's just at that moment, you're going upwards for that moment. So increasing intervals will have a positive slope. That should imply something. It should imply that a decreasing interval will have a negative slope. Let's look at our decreasing interval. There's only one of them. Is the slope negative for our entire decreasing interval?
Yep.
Let's check it out. Use your hand or your pencil if you want to. Here's our decreasing interval. Here it's at 0 right at B. But as we go past that, is that negative? Negative? Even when you get down to here, it is still negative, but then it's becoming still negative, but less negative until we get down to that point. At this point, look what happens. what's going to happen when we change from decreasing to increasing? What happens to our slope? As we change from decreasing to increasing, our slope goes from
Negative to positive.
negative to 0 to positive. Does that make sense to you? From increasing to decreasing, we go from positive to negative. And we're going to incorporate all this stuff into our graphing of functions in just a little while. So right here, we need to know that a decreasing interval will have a slope which is negative. Definitely negative slope. I'm going to write out what I just talked about. So this is nothing else than what I've just described. This implies a couple things. It implies that if our, what will a slope again? How do we find slope in calculus? What gives us a slope?
Derivative.
If our derivative is greater than 0, if our derivative is greater than 0, that means our
Positive slope.
slope is positive. Is our function increasing or decreasing?
Increasing.
If f prime of x is greater than 0 on an interval AB, then my function is increasing. On that interval. You can see from our examples, this is definitely increasing, right? Our slope is positive at every single point, from A to B. Positive. Every one of those slopes at every single point is going to be positive. That's all this says. This says in English, here it is in English for you. If the slope, right? If the slope's positive, you're increasing. That's all it says. You guys understand that idea? If the slope's positive, you're increasing. If the slope is negative, then f of x is decreasing on the interval. You still okay so far? In English, again, what this says is, if your slope, remember first derivative slope, if your slope's negative, you're decreasing. That's all it says. The last case is,
It's constant.
if f prime of x, if your derivative equals 0, so your slope is 0, what that says is that, well, if your slope's 0, you're constant at that point or on the interval. So for instance, right here at B, our slope is 0, right? That means we're not increasing, we're not decreasing, we're constant right there. That means a horizontal line, true? Constant means a slope being constant means horizontal line. So if we have our f prime of x equals 0, we're talking about a constant line right there. That means for us a change, typically that's a change from increasing to decreasing, or from decreasing to increasing, or that we're constant. That's what we're talking about. What's very cool is that we don't need a graph to do this. With just a function, if we know how to find the derivative, you can give me the intervals of increasing and decreasing. we're just going to be having this set equals 0 and do what's called the sign analysis. I'll teach you how to do that as we go on in the next sections. The last thing we need to talk about in increase, decrease, and concavity is, well, of course, concavity. Concavity is the direction of the curvature of your line. Or the description of the curvature might be a better, I'll say direction, but. Or basically, it's how the slope is changing. Now you're gonna, I'm gonna try to match this up for you right now. You know this first derivative means the slope, correct? How the slope is changing, that's a rate of change of the slope, should be a what type of derivative? Second derivative. First derivative gives you slope. Second derivative gives you how the slope is changing, a rate of change of the slope. And so when we're talking about concavity, you're going to find out in just a second, concavity has to do with the second derivative. First derivative gives you increasing and decreasing. Concavity gives you the way that you are curved, the direction of curvature. That's the second derivative. So basically it's how a curve is increasing and decreasing. Let me give you an example about why this might. Basically, it's how a curve is increasing and decreasing. Let me give you an example about why this might kind of be important for you.
Acceleration.
Would you agree that to get from this point to this point and be continuous, that you are going to be increasing on this? Okay. And let's just pretend that we're not going to go up and down. Let's go from here to here and not go back down again. So we'll definitely overall be increasing from here to here, right? Is there more than one way to get from here to here? Well, and still be increasing? Sure. You can probably think of it. I mean, I'm going to be kind of simplistic about this. You could be straight, right? But that's not fun. You could do that, couldn't you? But you could also do that. Those have different curvatures. Here's one type of curvature. Here's another type of curvature. Here's one that's increasing at an increasing rate. Do you see what I'm talking about? It's starting to go up, and it's going up faster, faster, faster. Here's one that's increasing at a decreasing rate. It's going up, but it's going up slower, 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 and finally gets there. Right? Increasing at an increasing rate. The slope, look at the slope of this. Here's my slope, right? My slope is positive for every point. Do you understand? But my slope is positive here, but it's even higher and higher and higher and higher. My slope is actually increasing. Do you see what I'm saying? The slope is increasing. Here, this is increasing, but the slope is actually decreasing. The slope is going downward. What that does is gives us a curvature, notice, really positive, but at the end, not so much positive. What it does is gives us how our curve is shaped. That's basically it. So concavity is the curvature of our graph. And right now, I really just need you to get to be familiar with concavity, what's concave up and what's concave down. So we'll talk about that for a little bit, and hopefully get on to how to find these out from just functions. This function is increasing everywhere. True or false?
True.
Definitely true. It's always going up. Is it going up at the same rate?
No.
No. In fact, you'll notice this. This is going up at an increasing rate. Oh, wait, and then something happens, doesn't it? And then we're level, it looks like we're even for a while. And then we start increasing, but at a decreasing rate until we get to the top. See what I'm talking about? This is our two different types of concavity we have. One region of this is going to be called concave up. If the curve is increasing at an increasing rate, that's this way, this is going to be concave up. Your slope is positive. This is going to be concave up. Your slope is positive. Your slope is increasing. Actually, that's all we need is really the slope is increasing. The slope is increasing. That's going to give you a concave up. Concave up. Concave up. You okay with that?
Yeah, is it concave?
Well, what I'm saying is concave up doesn't have to be increasing or decreasing as far as the function is concerned, but the slope must be increasing. I know this is going to be kind of weird for you to wrap your head around, but this is a completely concave up shape right here. Would it hold water?
Yeah.
Concave up will hold water. Also, how do you feel when you're happy, when you're up, when you're feeling up? Like you smile. You're feeling concave up. Happy. Like concave up is going to hold water, it's going to be upward facing. Now, if you're confused as to, Mr. Leonard, why did you say that the slope is increasing? The slope is increasing here. Watch. What's the slope here? Very negative. What's the slope here? A little less negative.
True.
We're not talking about the function, we're talking about the slope of the function for concavity. What's the slope here? Very negative. Less negative, less negative, less negative, less negative, 0, positive, more positive, more positive. The slope is actually increasing the entire way through. Do you see the difference? It's difficult to think about because I haven't graphed the slope, I've graphed the function. But we're talking about the slope and how the slope is changing for concavity. There's the distinction. So this is definitely concave up. That's concave up. What it says is it opens upward. That's how people describe it. It opens upward. Or it would hold water. That's probably the worst one. Here's what it actually means in mathematics. If you're concave up, it means your slope is increasing. The function is not necessarily increasing. We see that. This is actually decreasing, but the slope is increasing. Do you see the distinction there between increasing and concavity?
It's like negative.
The slope is increasing on that interval. That's what concave up means. You okay with this so far? Okay. What's concave down look like? Feeling down. Down. Concave down, Friday face. It's your umbrella. Water slides right off it. Opens downward, would not hold water, but really what it means is that your slope is decreasing. Your slope is, whether your function is increasing or not doesn't matter for concavity. Concavity says how's the slope changing? The slope changing for concave down means it's decreasing. Slope is decreasing. Notice, look at it. How's this curve go? Yes, the curve itself does this. What's on the board here real quick? Notice the distinction. The curve itself is increasing and then decreasing, yes? But the slope does the same thing the whole time. The slope is very positive, less and less and less and less and less and less, 0, negative, more negative, more negative. It's always decreasing through the whole entire curve. You see what I'm talking about? There's a difference between increasing and decreasing as far as the slope is concerned. There's a difference between increasing and decreasing of a function and the slope, how that changes on a function. Now, here, can you tell me where my intervals are for increasing and where my intervals are for decreasing? Stop me when I, for my slope, stop me when I change from concave up to concave down. What do I start with from, let's start this way. What do I start with here, concave up or down?
Up.
And, oh, you
Down.
missed it. Let's try that again. Ready? No, I'm just kidding. And, yeah, somewhere in here. Now, exactly where, I don't know, because I don't know the function itself, but it's gonna be somewhere right about, I would say there. Right about there, we change. We change from holding water to being an umbrella, from being concave up to concave down, from the slope increasing, and slope dies off, decreases. Do you see what I'm talking about there? That changes from concave up to concave down. This would be up, concave up, concave down. This point, where you change concavity, is called an inflection point. Inflection.
I've heard of this before.
Or point of inflection. That's your inflection point. Well, we're going to continue talking about increase and decrease.
stop here.